Hello everyone, welcome to this video lesson. In this video lesson, we are talking about mechanical properties of solids. We are going to deal with a problem or a concept. It is like this. The concept is like this. We need to identify the elastic nature of a material of the wire basing on the stress and strain graphs. Let me tell you how does a sample graph looks like. Say for example, there is a graph like this. Say this is origin, this is x-axis, this is y-axis. Assume stress is taken on x-axis, strain is taken on y-axis. The stress and strain graph for three different materials is drawn like this. This is for the material A, this is for the material B, this is for the material C. The question is simply who is more elastic and who is less elastic in A, B and C. That's what the question is. Look at the graph. The graph is taken between stress and strain. If I find the slope of any graph, slope of the graph is nothing but equal to tan theta. So tan theta for this graph is automatically, opposite side by adjacent side. Opposite side is nothing but equal to strain. Adjacent side is nothing but equal to stress. We know stress by strain is Young's modulus. Strain by stress is 1 by Young's modulus. Therefore, slope is 1 by Young's modulus, or in the other way, slope is inversely proportional to Young's modulus. Means what? What's the meaning of that? If a wire has more slope in the graph, it has less Young's modulus. That means it is obviously less elastic in nature, because Young's modulus is a measure of elastic nature of the material. So it's very clear. If I call this slope as theta 1, this slope as theta 2 and this slope as theta 3, it's very clear that from the graph theta 3 is greater than theta 2. Theta 2 is greater than that of theta 1. That means as the slope is inversely proportional to Young's modulus, the one who is having a least slope will be having a highest Young's modulus. That means Young's modulus of A is more than that of Young's modulus of B. That's even more than that of Young's modulus of C. That means here wire A is more elastic and wire C is least elastic. This is how people can give you a question basing on stress and strain. Let us go to some another graph. Suppose you have a different kind of a graph. That the graph is like this. This is origin, x-axis, y-axis. Instead of stress here, assume a strain is taken here and the stress is taken here, and the graph is like this: A, B and C. I would like to calculate again who is more elastic and who is less elastic here. How can we identify? Again, this using the same logic that I will try to find out the slope of this graph. Slope of this graph is again equal to tan theta. That's nothing but equal to opposite side by adjacent side. Opposite side is now stress to this angle theta. Say theta 1. Adjacent side is strain. So stress by strain is Young's modulus itself. So it's very clear. Slope itself is Young's modulus. or slope is directly proportional to Young's modulus. So the wire who is having higher slope is more elastic. You must have noticed it is reverse to that of a previous case. So this is theta 1, this is theta 2, this is theta 3. From the graph, it is very clear that theta 3 is greater than theta 2 is greater than theta 1. That implies as Young's modulus is directly proportional to slope, Young's modulus of C is greater than that of Young's modulus of B. That's even greater than that of Young's modulus of A. That means here C is more elastic and A is least elastic. This is how we can find out the elastic nature of the material basing on the stress and strain graph. Thank you for watching. Keep coming back for more and more video lessons. Thank you.